Okay, here we are, Chapter 2 of Physics 125. Chapter 2 is about problem solving. Again, as I mentioned, there will be several chapters here at the beginning that will be about gaining the skills we need to be able to do physics effectively. So one of the very important skills we need is the ability to solve problems. And this goes way, way, way beyond physics, but it is something that we need in physics, not only in the class, but in order to do physics in general. And there's a partial definition here on the first slide, the process of working through the details of a problem to reach a solution. And that's going to be one of the big messages that I'm going to share in problem solving is that, maybe when you had math classes in high school or in grade school, you'd come to a problem, a story problem or something, and you'd look at it and you'd just be like, I have no idea how to do this. And so one of the critical skills we need is to be able to take a big problem and break it down into smaller problems and be able to attack it in little pieces. And very often then we will be able to work through the entire problem. So again, in this class, we're going to need it in order to solve the mathematical problems. We're going to use formulas and principles to do our problem solving here, but in life, the problem solving ability is super important. There's a quote here from somebody, I don't know who Martinez is, but basically saying that in the 21st century, as society changes, as technology continues to expand, you're not going to be able to learn some skill in college and then go, okay, I'm going into a career, I'm going to spend 35 years doing this same thing. Not going to happen. Things are going to change way too fast. The process control world has changed a ton. My dad entered the refining business in the 1970s and they had no computers. And now a lot of process control is looking at the screens and monitoring things through the computer. So the change has been immense over time. And really, this is ultimately, you look across fields, you look across different careers. Ultimately, this is what you get paid for. This is what you get paid a lot for, is the ability to solve problems. I remember when I was in high school, I worked at McDonald's. I was just an hourly employee. And anybody who came to the counter and was upset, anybody who didn't like the food they got and whatever, the solution was always the same. Here, let me get my manager. You can talk to my manager. The manager's job was to resolve that customer service issue. And for a while, they thought that I would make a good manager. And I looked at them and said, you know what? The manager's making $2 more an hour and they're dealing with a lot more headaches. No thanks. I'd rather be the peon. I'd rather flip the burgers and take the orders and not have to deal with the headaches. But the reality is, if we want to get paid as a professional, we have to be able to solve problems in a particular area. Doctors, what do doctors do all day? People come in, people describe symptoms. The doctor's job is to problem solve, to figure out what is causing those symptoms and then what the best way to treat them or treat that underlying condition would be, right? Lawyers, their job is to solve problems, right? Problems of the law. Somebody has an issue and they'd like to know how to change things. And the lawyer's job is to try to figure out what law would apply and how he can get the outcome that his client is interested in, right? In physics, I talk to my students a lot in my high school class in particular about the potential to be engineers. And many of them look at me funny and they say, well, people have told me I'm good at math and I'm good at science, so I might be a good engineer, but I don't really know what an engineer does. And the answer is the engineer's job is to solve problems, problems of manufacturing, problems of design, problems of repair. All those things ultimately fall on the engineer, and it's his job to provide a solution. Now, sometimes we get frustrated if we're working with an engineer and the engineer says, well, just do this, and we're the person who would have to do it, and we know that the details of that is not going to work. But ultimately, if you want to get paid more in life, the goal of the skill that you really need is problem solving. So that's what we're going to talk about in this chapter. More in this chapter about the first bullet point, how to solve problems in physics, but ultimately this is a super important skill for life and for success in any career. So we're going to use variables and formulas in this class quite a bit. And some people go, why? Why must we use letters? What's the point of algebra? It's all ultimately going to be about numbers in the end. So why do you stick letters in there that we're just going to replace with numbers? Well, the point of variables, which again are symbols that represent numbers, is that we can study the relationship. We can see the pattern that's going to apply in many circumstances and not just with these particular numbers. And so I've got an equation up there, F equals ma. We'll find a lot more about that in chapter 5 when we start talking about forces, but it's one of the more famous equations in physics, and it really contains a lot of information just in a few letters and one equal sign. A lot of critical information is there, and we will actually solve numerous problems using that equation, in which we will actually stick in numbers. But to study the relationship, the equation with the variables is much better, because again, the power of variables is to say it doesn't matter what the force is, what the mass is. This is always going to be the relationship between the force, the mass, and the acceleration. And so that gives us power to apply it in many different circumstances. And again, it's about representing real physical relationships, right? We are not mathematicians. We don't make numbers up. We don't make up relationships. This is all coming from the real world, from real physics. So a simpler one that we're perhaps more familiar with, the idea of velocity times time equals distance covered, right? So if I drive down the highway at 70 miles an hour and I drive at 70 miles an hour for 3 hours, then how far will I go? Well, at 70 miles an hour, that's a velocity, that's a rate at which we're covering distance, 70 miles each hour. And if we do it for 3 hours, we need to multiply those together to get our answer. So velocity times time equals the distance covered. So 70 miles per hour times 3 hours will equal 210 miles. That is how far we will cover. So that works for those particular numbers, but it works in general. Doesn't matter whether you're going 70 or 50, doesn't matter whether you travel for an hour or a half an hour. That's how we're going to calculate the distance that we travel. So this is often how I will introduce equations in this class. I'll write it out once with the words velocity times time equals distance covered. And then we'll move pretty quickly to the symbolic representation, right? The nice thing about physics is there's a number of formulas, but we tend to reuse the same inputs over and over again, right? Time's a big deal, and velocity is a big deal, and distance is a big deal. So we'll end up seeing a number of different equations that involve velocity, time, and distance. And so it becomes pretty easy to recognize what those individual variables stand for. We like to use a single letter as our variable. Sometimes we'll use a letter and a subscript to be more specific about that variable, but we don't like to use two-letter variables. So VT would not be a single variable. It would be two separate variables, V and T. Sometimes looking at the equation and thinking about the extremes can be very helpful, right? If my time is 0, it doesn't matter how fast I'm going, right? It doesn't matter how fast of a car you have. If you don't spend any time traveling at that velocity, you won't get anywhere. Or you can think about it the other way around, right? If my distance is very large, I'm going to need a large velocity and a large time to get there, right? If I want to travel to the next star, the distance is enormous. So even if I can get a spaceship that goes really, really, really fast, it's going to take a really, really, really long time as well. And if your velocity is 0, it doesn't matter how long you travel, right? You got no tires on your car. It doesn't matter how long you sit behind that wheel. You sit there for days. You're still not going to go anywhere because your velocity is 0. So again, how do we use these formulas? They help us look at the problem instead of the number, and we're going to start solving the problem with the equation, right? Some people, they see an equation, they immediately want to stick their numbers in, and that's not really the best way to do it. It's better to do your algebra with the variables until you've got it all solved for what you're looking for, and then to stick in the numbers. And we're going to do a very simple example here, but this becomes much more important with more complex variables or with multi-step problems. So how long does it take to go 500 miles if you are traveling at an average speed of 70 miles per hour? So there's a fairly simple but a typical physics problem, right? They've given us some information, 500 miles and 70 miles an hour, and they've asked us a question: how long will it take? So part of the art of solving physics problems is being able to interpret the words into the right items, right? So 500 miles is a distance that's fairly intuitive to us. We're familiar with the unit of miles. We know what that means. Likewise, miles per hour is a speed or a velocity, and it tells us that here as well. So we can identify those two. One of the challenges sometimes is to interpret how long, right? We might think, well, how long? That's an easy English phrase to interpret, but that can sometimes, as in this case, mean how long in terms of time, right? How much time will pass, but how long can also be, how long is the meter stick? It can be a distance. So sometimes we have to be careful in reading the problem and taking the context. Now, they just gave us another distance, so it's unlikely that this question, how long, is a distance, because they gave us another distance. And those are the types of clues that you're going to use within the problems to figure things out. Now, life is really simple right now because I've only given you one equation. So obviously, we're going to do this problem with the one equation that we already have. In a typical chapter, it's going to be a little more challenging. We're going to have somewhere between a half a dozen and a dozen equations that we're using in this chapter or from this chapter in the previous chapters, and it's going to be a matter of deciding which is the right equation for the problem. But that's part of the problem-solving process, is to identify the appropriate equation so that we can solve the problem. So this is going to be our equation, right? Distance equals velocity times time. But we're being asked for the time, right? And as we see, this equation it's solved for something. It's solved for d, but it's not solved for t. So this is the point here of this slide in this discussion, is we want to solve for the t before we stick our numbers in. So we do that, right? Common algebra, if we want to get the t by itself and there's something multiplied by the t, our solution is to divide by that something. So vt divided by v, that v will cancel out, right? This is a basic algebra principle that if you have something in the numerator and in the denominator, it will cancel out, because anything over itself, 1 over 1, x over x, 50 over 50, that is going to give you a fraction of 1, and it's anything equal to 1 can simply be written as 1 instead of as those values. So we divide this side by v, and whatever we do to the right side of the equation, we must do to the left side of the equation. That's necessary because we have an equal sign, right? And in order to maintain equality, we have to do the same thing to both sides. So we divide both sides by v. This v cancels out, and we divide by v over here. And so we end up with t equals d over v. Now we have solved our equation for the answer that we're after, and now we can plug our numbers in. So we stick 500, step back, 500 miles in for our distance, 70 miles per hour in for our velocity. Okay, now I stuck the units in there, and we're going to spend a fair amount of time discussing units in this chapter. Units are very important in physics and in science in general. Units are not super important to the mathematician, right? The mathematician is very focused on the numbers, and oftentimes those numbers don't come from actual measurements, so the units are less important to them, which is why I think sometimes my students who are very strong in math struggle in physics, because that unit piece, they're not used to having to worry about very much. So 500 divided by 70, we could do that. But what do we do here with the units? Well, we have miles in the numerator, and we have miles over hours in the denominator. So we do have miles over miles, so those are going to cancel. But then what does that leave us with? That leaves us with nothing, which we say 1. 1 over hours. And what is that? Well, if we have 1 over hours and we multiply it, remember, we can always multiply by something equal to 1. And that we don't have to do to both sides, right? Because something equal to 1 is equal to 1, and anything times 1 is itself. So we're not changing the value of the equation by multiplying by something equal to 1. So what we're going to do here is we're going to multiply by hours over hours. An hours in the numerator and an hours in the numerator of the denominator, okay? And this reinforces the idea that any unit that you have by itself is really in the numerator and is over 1. So hours over hours. Then we'll have hours over hours in the denominator, and those will cancel. And we will just have hours in the numerator. So 1 over hours, we end up with the units of just hours, which is what we want, right? We're trying to solve for a time. A time should come out in a unit of, an appropriate unit of time, which hours is. So this is just a discussion of what's happening with the units and why when I do miles divided by miles per hour, I end up with an answer of hours. So 500 divided by 70 comes out to be 7.14 hours. So if I travel to my in-laws when the coronavirus restrictions are lifted and my in-laws live 500 miles away and we travel on the interstate and average 70 miles an hour, it will take me a little over 7 hours. It's assuming, of course, that none of my children need to stop and go to the bathroom, which is optimistic. So how do I make sure that I don't screw up this formula? I get this question a lot from students. I get a lot of students who tell me that physics is hard and difficult, and it's all physics' fault that it's hard and difficult. And as I look over their work and I check their problems, I say, you know what, you really don't have a problem with physics. You understand the physics concepts. You understand how to translate those concepts into mathematics. Your problem is that you make too many mistakes when it comes to math. And that's a challenge in physics. It really is. You know, if you take a math class and you mess up one problem in 10, that's 1 out of 10. That's 10%. You get a 90% in the class, you get an A. But in physics, sometimes we are doing multiple mathematical steps in a problem. And so maybe you've got to do 3 distinct algebra steps to solve a physics problem. Well, if you're messing up 1 in 9 of those or 1 in 10 of those, that's basically going to cause you to get every 3rd problem wrong. And if you get every 3rd problem wrong, then you got a 66%, and that's a D. So people say, well, wait a second, I got an A in algebra. Why am I getting a D in physics? So how can you say that my problem is algebra? Well, again, that's the situation. You have to use your algebra a lot. You have to be very proficient with it, and you have to have a high level of skill at getting it correct all the time. So some things to help us when we tend to keep us from making some of those mistakes. And one of them is the units, which we just discussed on the previous problem. If we do the math that we do to the numbers, to the units should come out correctly. And sometimes when we do the math incorrectly on the numbers, and then we do that same math to our units, the units can tell us that we did something incorrectly. So here's a more complicated problem, complicated equation. Distance equals your initial velocity times time plus 1/2 of your acceleration times your time squared. So this is essentially the equation we'd seen before, but it's for an object that's not moving at a constant or average velocity, but is actually accelerating. The details of this equation are not important. We will get into where it comes from and what it means more in chapter 4. But I'm just looking for a more complex example to explain the type of mistakes that people will sometimes make. So they take their initial velocity, they multiply by their time, and sometimes they forget the 1/2, and this will not save you from forgetting the 1/2 because the 1/2 doesn't have any units. But what often happens over here is they just do A times T, and they forget that they're supposed to square the T, and that's often what causes people to get a problem wrong that involves this equation. They're forgetting to square the T. So if you would do to the units exactly what you did to the numbers, you would see that there would then be an issue if you forget to square, right? Meters per second, velocity is in meters per second, time is in seconds over 1. So our seconds would cancel, and this piece would be in meters, right? And we're solving for a distance, so we want our answer to be in a unit of distance like meters. We come over here, acceleration is meters per second squared, and if we only have 1 second here, ignore that 2 for a moment. If we only have 1 second here, then it only cancels 1 of those seconds in the denominator, and so we would end up with meters plus meters per second, and that should be a big warning bell, right? You can't add things that have different units. You have to add things that have the same, yes, you can add feet and inches, but those are both units of distance, right? And you can convert one to another, but you can't convert meters per second into meters. One's a velocity and one's a distance, and you can't add distance and velocity and have any kind of meaningful answer. So what we needed to do was to square our time, and when we square our time, we square our units. So we have meters per second squared for acceleration, and then we have seconds squared for our squared time, and all those seconds cancel. And so then we have meters plus meters, and that's appropriate for our distance. So if we stuck some numbers in here just to do some mathematical practice, we have an initial velocity of 3 meters per second, an acceleration of 4 meters per second squared, and a time of 3 seconds, right? So we stick those in. We have 3 meters per second times 3 seconds. So those seconds cancel. We get 3 times 3, which is 9. And then we have 4 meters per second squared, and we have 3 seconds squared. So the squared seconds cancel with those squared seconds. We have 4 times 9, 1/2 of 4, which is 2. 2 times 9 is 18. 9 plus 18 is 27 meters. So that's how you would solve this problem for the distance. All right, so now I'm going to go through a process that has 9 steps, a problem-solving process. And I recognize that, this kind of seems like a lot of steps. And the reality is a number of these steps you're going to do mentally as you go through the problem, and you're not necessarily going to write anything down from the steps. But I just would encourage you to come back to this, whether you write this down on your own or whether you just come back to the PowerPoint, to come back to this process when you are working on hard problems in later chapters. When you have a problem and you go, wow, I just have no idea where to start. And again, when I'm helping students, I get that response a lot. I got this problem, I have no idea what I'm supposed to do. And I say, well, you have a lot of information already. And if you just start working the process, sometimes what to do will become obvious. And really what they're saying as we go through these steps, they're saying they don't know how to do step 5. They don't know which equation to use to solve. And I understand that. Sometimes we see a problem and we're just not sure what the right mathematical approach is. But if we go through this process, if we work the process, oftentimes that step becomes easier if we've done the steps before it. And I got the little image up here on the top about the journey of 1,000 miles begins with a single step. And it's very true. And if you do these little steps at the beginning, it can make the harder steps in the middle and the end a lot easier. So the first thing you got to do is read the problem completely and reread it. Again, oftentimes physics problems are a little involved, right? But the beauty of them, what I love about physics problems as opposed to chemistry problems or even typical cellular biology problems, is that they're about things that we can often visualize, right? It's about a ball flying through the air, or it's about a couple of people pulling on a box. It's things that we can, in fact, visualize. It's not super tiny atoms that we've never been able to see. It's not cells that we also have never actually seen a real one of. So a lot of physics is intuitive in that way. And so that's wonderful. But you got to read the problem carefully and completely. Again, I can't tell you how many times I've come over to help somebody with a problem, and the issue is they misread the problem. And if you misread the problem, if you don't have the correct inputs, then you're going to be in a the problem's going to be impossible to solve if you didn't read it correctly and you have the information wrong. So read the problem, and then again, make a sketch. Many of these things are things that we can physically envision. So just make a quick sketch. Doesn't have to be fancy, doesn't have to be pretty, but just what's going on, some arrows that would indicate the motion or the direction of the forces or that sort of thing. Again, the sketch can sometimes lead us to information that's inferred, but not written directly in the problem. And then step 3, really important. And again, like I said, I come to help people and they say, I have no idea where to start. And I say, hey, the least you can do is write down, what do we know? What numbers did they give you? It's going to be an extremely, extremely rare physics problem that isn't going to give you some numbers to start with. Okay, so let's look at the problem. Let's write down what we know. Let's list them as givens that we've been given with the units. And this is also very important that we recognize what the given is, right? So a couple slides ago, we did a problem with 500 miles, right? So we would write down 500 miles, but we'd also write down D equals 500 miles because 500 miles is a distance. And that's what's going to be important when it comes time to choose a formula, is to know, what quantities are we working with? Do we have a distance? Do we not have a distance? Are we solving for a distance? All of those good things. So we write down what's given, which is usually the numbers in the problem. But then, as it says there in yellow, there's also non-numerical statements sometimes that are really important, like from rest. If something's starting from rest, then that tells us that its initial velocity is 0. And if we can interpret those words in that way, that gives us another variable, another tool that we can use to pick the right formula. Or constant velocity would tell us that it's not speeding up or slowing down, which means something called acceleration is 0. And when I made the mention about the sketch, for example, something going straight off of a cliff, you would then from the sketch be able to realize, oh, if they are going straight off the cliff, then that means they're only moving in the horizontal direction. They're not moving up or down. And that's other important given information that you might infer from the sketch. or perhaps a different problem where it's talking about somebody kicking a ball down a football field. And you make that sketch and you realize, oh, well, whatever height the ball left from is also the height it's going to return to the ground at. It's not going to gain or lose height in terms of comparing the launch point from the landing point. So those are things that you're going to be able to infer from the sketch. And again, obviously we'll do practice problems. This is not stuff that that you're expected to infer without any practice, but it's important steps in the method that will help you to get this information. So step 4 is super important too, right? Again, I come over to a student and they're like, I don't know how to do this problem. And I say, well, what are you solving for? And they say, I don't even know what I'm solving for. And if you don't know what you're solving for, you're in big trouble. You're never going to get there, right? There's the famous quote, if you don't know where you're going, you can't possibly get there, right? If you don't have a destination. And the same is true in the problem solving process. So again, that previous problem that we did, it said, how long will it take? So to interpret those words and realize that they're asking for a time. Again, there's often a question mark somewhere in your problem, and that question mark relates to what you're supposed to be solving for. What's the unknown? And sometimes there's multiple unknowns. Sometimes there's an intermediate unknown. I need to use the information they gave me to find this intermediate value, and then the intermediate value will help me find the final unknown. We don't do a ton of that in this class, but we do some of that. So finding the unknown and writing it down. I like to write it down with a big question mark next to it. So I'd write T equals question mark. And then I would know I'm solving for the time and I don't know the time and I'm not supposed to know the time yet. That's the unknown that I'm solving for in the problem. Now, step 5 is, again, what people usually mean when they say, I don't know how to solve the problem. They say, I don't know which equation to use. I don't know how I'm going to get from these knowns to the unknown. But again, if you've made a list, if you've said D equals 500 and V equals 70 miles per hour and T equals question mark, and you have all those written down right next to one another, that can be extremely helpful when it comes time to choosing the right equation. And again, memorizing equations is not what's important in this class. There'll be a formula sheet. I'll provide you with a formula sheet for each of our exams. You're going to do your homework and your quizzes, open book. It's not a matter of having to memorize a bunch of equations. It's perfectly acceptable to look at your list of equations and try to decide which one to choose. And ultimately, your goal is to pick an equation that has both your knowns and your unknown and nothing else. That's important, right? If I have, like we just said, if I have D and V and I'm looking for T and I find an equation that has an A in it, that's not helpful, right? Because that's acceleration and I don't know my acceleration and I'm not supposed to be finding my acceleration. So I just want to avoid an equation that has an A in it because I don't know it and I don't want to know it. And so it's not a useful equation for me. And again, in this class, this is Introduction to Physics. A lot of times there's gonna be an equation sitting there that has your knowns in it and your unknown in it and nothing else. And then that's the one that you're gonna go with. So once you've chosen your equation, you want to do some algebra to the equation to solve it for the unknown quantity, like we did in the previous problem where we solved for T, which was our unknown quantity. This is sometimes called the working equation. You're working with it, manipulating it, still in the algebra form with the variables. Then we plug our numbers into that equation, including their units, and we do the math to the numbers and to the units. We do our actual calculation, like I said, with both the numbers and with the units. And then we take a moment to think about our answer. Does our answer make any sense? Again, as a teacher, I've experienced this many, many times where people come up with an answer that it doesn't really make any sense, right? They talk about a satellite that's going to orbit the entire Earth in a fraction of a second. That's not very good common sense. Or the problem we just did, right? If you calculate that you're going to go if you're going to go 500 miles in 0.7 hours in a car, that's pretty unrealistic, right? So we just want to do a common sense check, which again can often be done because these are very these are situations that we have some real life experience with, right? I couldn't tell you what a common sense answer would be for the radius of an atom because I don't have any good sense of what a radius of an atom is. But I can tell you that to go 500 miles should take me multiple hours in a car, right? Not multiple minutes, but multiple hours. It probably shouldn't take me multiple days, but it should take me multiple hours. And just that type of common sense check, and of course, checking your units that they came out appropriately for an answer. So it's a little challenging to do practice problem solving in physics when we haven't learned any equations yet. So we're going to do a combination of some physics equations, and we're going to do some just area and volume basic shapes equations. So this slide is here just to give you a set of equations to choose from when we go to subsequent slides and we start doing some practice problem solving. Because really, that's the upshot of this chapter, right? The point of this chapter is for us to learn how to problem solve and for us to practice problem solving so that we're good at it by the time we start doing physics. So the rest of this PowerPoint slide is going to be me talking through problems. Actually, what it's going to be is you pausing the video, trying the problem, and then hearing me work through the problem according to our 9 steps. And again, we're not going to always do all of the steps explicitly with something written down, but we're going to at least think through all the steps as we go through the problem. So if you want to take a moment to copy these down or to print this slide off so that you have it available to you as you do some of these problems, you can go ahead and do that. Again, these PowerPoints are on a Blackboard along with these videos so that you can have access to both in a form that's useful. So here's our first problem solving practice problem. We're being asked, what is the volume of this object? So we have a number of pieces of data that are drawn in on the sketch, and we have a sketch drawn for us. So it's a rectangular tube. So there's a hole that goes through the middle, and it's rectangular, the hole's rectangular, and the whole tube is rectangular. So what is the volume? Again, you can go ahead and pause the video and work through this problem on your own. And then I'm just going to go right into solving the problem. But I would strongly, strongly recommend that you don't just go, oh, well, I'm watching the lecture, I'm just going to watch it all the way through. The key to this is to practice, and you've got to practice on your own without having the answer in front of you for it to be legit practice. So pause the video, try this problem, get your own answer, and then watch me work through the problem. And maybe you got the answer right, maybe you didn't, but if you tried and failed, then the correct explanation will be so much more useful than just watching the correct explanation and thinking that you're going to absorb the skill from watching somebody else do it. That's really not a very reasonable expectation of how to learn. So the first 3 steps, we're supposed to read the problem. This is a very short read problem. What is the volume? We're supposed to copy down the sketch or make a sketch. In this case, they had a sketch for us, so making a sketch on our own is super critical. And then we need to write down all the numbers that we've been given. Well, they put the numbers directly on the sketch. So steps 1 through 3 were sort of done for us and don't really need to be redone or recreated necessarily. So steps 4 through 6, we need to identify the unknown. Well, the identifying the unknown is really easy in this problem because the problem is literally one sentence, and it's what is the volume. So our unknown is the volume of the object. Okay, now what equation are we going to use to solve this problem? So we have a couple of volume equations. This is not a triangle. This is rectangular, so we would have length times width times height, but there's a hole in the middle. So a couple ways we could do this. We could find the volume of the whole tube, and then we could find the volume of the hole and subtract the hole from the whole tube, from the entire tube. Or we could find the area of the base, right? If we find the area of the end of the tube, and then we could just multiply that by the length of the tube, and that would give us a volume. So that's the approach that I'm going to take. The area of the base, which in this case, the base is a vertical face, right? So I'm going to find the area of just the end of this. We did a problem similar to this in chapter 1. And then I'll multiply that total area by the length of the tube, which is 12 centimeters. So I've identified my unknown. I've identified what equation I'm going to use to solve for that unknown. And that equation is essentially is already solved for volume, right? It's going to be total area times the length to give me the volume. So step 7, I'm going to plug the values into my working equation, right? So for my base area, I'm going to take the total area of the end of the rectangle. So that's 9 tall. That 9 refers to the total height. And 6 wide, this 6 refers to the total width. So 9 times 6. And then the whole is 6 tall and 3 wide. So 6 times 3. So 9 times 6 minus 6 times 3, that's 54 minus 18. It comes out to be 36, right? And then we're going to multiply that by the 12. So 54 minus 18 is 36. 36 times 12 is 432 centimeters cubed. Again, use a calculator. Absolutely use a calculator. There's nothing in this class that says you need to be able to do math in your head at all. Trust your calculator. You'll always have access to a calculator to solve these problems in this class. And the reality is in real life, you're going to have access to a calculator to do your basic math. So that's my answer there in step 8. It came out to be centimeters cubed because here it was centimeters times centimeters, which is centimeters squared, and we're subtracting centimeters squared. So that answer, the 36, came out in centimeters squared, and then the 12 is in centimeters. So centimeters squared times another centimeter will be centimeters cubed, and volume should be in cubic units. So that checks out. Now my common sense check. How do I do my common sense check? Well, 12 is about 10. And if this is 9 times 6, but there's a hole, so 9 times 6 is 54, but we've got some kind of hole. So let's call that 10 by 5. 10 by 5 is 50. 50 times 10. See, this part I can do in my head. 50 times 10 is 500, about 500. Is my answer about 500? Yeah, it's about 500. I mean, it's less than 500. It's less than 500 by more than 10%. But that's an order of magnitude, right? I didn't calculate that my answer should be about 50 and get an answer of 432. I didn't get that my answer should be about 5,000 and got an answer of 432. I got that my answer should be in the hundreds, in the mid hundreds, and I got an answer in the mid hundreds. So I'm going to call that a successful common sense check, and that's going to be an acceptable answer for me to write down on my paper. So again, you might have done this problem much faster than this. You might have done the problem slower than this. Again, as we practice, as we do more of these, you'll get faster at them. You might be faster than me already at this point, but I'm working through the steps so that we can get into the habit of following all these steps and not skipping any of them, and therefore having greater success. So here's our next problem. It's actually going to be a multiple step problem, not really multiple step, but there are multiple questions, right? They're giving us a building, they're giving us some dimensions of the building, and they're asking us to calculate the volume of the building, right? Very practical problem. Maybe you're trying to install an air conditioner in the building, and you need to know what the volume of the building is to know what size air conditioner to install. They also want to know how many bundles of shingles we're going to need to roof the building, and it takes 3 bundles to roof 100 square feet of roof. So I'm going to need to do some kind of calculation there. And then how many boxes of siding, if a box of siding has 200 square foot in a box of siding. So again, I would strongly recommend you pause the video, you work through this problem, see how you can do solving for all 3 of these answers. So first, the volume question, right? Here we have the building. Again, they drew the picture for us and they put the numbers on the picture, and they asked us a very straightforward and simple question. This first one, at least, is straightforward. So those are the first 3 steps. We read the problem, we drew the picture, we have the numbers, and we know what we're looking for. Step 4, again, we're solving for volume. Again, volume for something that's rectangular is length times width times height. or even if it isn't rectangular, as long as it's, you know, the same shape all the way along, we can find the area of the base and multiply it by the length. So that's again what we're going to do, because we have an irregularly shaped base, not terribly irregular, but there's a rectangle and a triangle on top of that rectangle. So we're going to find the area of the rectangle plus the area of the triangle, and then multiply by the length of the building, which this time is 37 feet. A little fast there. All right, steps 7 through 9, we're going to plug our values into our working equation. So this rectangle, the bottom part of the wall, is 22 feet wide and 10 feet tall. So 22 times 10 is 220. And then we have this triangle, which is also 22 feet wide, but is 4.7 feet tall and is a triangle. So again, triangle is 1/2 base times height. Equation was on our list. I'm missing a set of parentheses here. We need to add both of those areas together before we multiply by our length. It's correctly done down here in the calculation part. So 220 square feet times 51.7 square feet times 37 feet is going to give me 10,100 square feet. Again, following my multiplication rules. I didn't put all my decimals and my zeros in here, but everything here has 3 significant figures. So we should end up with an answer that has 3 significant figures, because we're doing all addition. I should say all multiplication. So we end up with 10,100 square feet. Again, our common sense check. This is 22 feet wide, 10 feet tall, plus the triangle. So let's call it 25 times 10. That would be 250. And let's call 37 40, because that makes the math easy. 250 times 40, 25 times 4 is 100, and then we got 2 extra zeros, so that would come out to be around 10,000, which our answer is around 10,000. And it's a volume, and it came out in cubic feet, so that's what we would expect and what we would want. So that was the first question, and now we move on to the second question. How many bundles of shingles do we need to roof it if 3 bundles per 100 square feet? So again, we have the same sketch, the same numbers. That part hasn't changed. This time we're supposed to be finding the area of the roof, right? We don't shingle the walls. We don't shingle the floor. We shingle the roof. So we need to find the area of the roof. There are 2 sides to the roof. Area is just length times width. They told us the height of a roof section is 12 feet. They told us the length of the building is 37 feet. But we do have 2 sides. So this is a simpler calculation. It's simply length times width times 2 for the 2 sides of the roof. My PowerPoint wants to go too fast. So 12 times 37 times 2 gives me an area of 888 square feet. But we're not done at that point, right? That solved us for the area, but we are ultimately supposed to be finding the number of bundles, right? So maybe I should have written bundles here instead of area, but the area is the intermediate answer that we need, right? We have to find the area to calculate how many bundles. So if we have 888 square feet, we divide that by 100. That gives us 8.88 squares, or 8.88 100 square foot sections. We need 3 bundles for each of those. We multiply that, it gives us 26.6. You can't buy a partial bundle, so we would need at least 27 bundles. But realistically, when you shingle, you have waste. Some of the shingles have to get cut off. Some of the shingles are stuck together inappropriately. So we add 10% to account for waste and other issues. So our 27 plus 10% is 3 more bundles. So we end up with 30 bundles total that we need. And again, some of those are practical considerations that you know of as a roofer, to know that you're going to need some extra. This is a real life problem. There's real considerations to go into it. You could order 27 bundles. You might be fine and not run out, but you might want to have a little extra. Again, the approximation, 12 is about 10, 37 is about 40. I rounded one down, I round the other up. 10 times 40 is 400, but we have 2 of them, so that would be 800. 800 checks with our answer. Siding, again, same problem. All the information has been given. We're trying to find this time the area of the walls that we're going to use to find how many boxes of siding. Area is length times width for a rectangle. So these the long walls are simple rectangles. The end walls are a little more complicated because we have the rectangular part and the triangular part. The nice part is that we already did that calculation for the first question, which was the volume, so we can just reuse that information. We have that 272 square feet for the end wall. We have 2 of those, and then we have 37 times 10, right? The walls are 10 feet tall, so 37 times 10 times 2. So we have a total of 4 walls, right? 2 that we can't see and 2 that we can see. The 2 end walls, front and back, the 2 side walls, blue shaded one and the one we can't see in the back. So we add all those together, we get the end walls give us 543 square feet, the long walls give us 740. We add those together, we get 1283. Divide that by the 200 square foot per box, and we have 6.42 boxes. Obviously, you can't buy 0.42 boxes, so we need to round up to 7 boxes. And we have more than, we're rounding up. We have to round up, you can't round down, right? Then you would be short-sighting. We're rounding up by more than half a box. So we already have essentially a half a box extra, so I wouldn't add any extra boxes to that. And then again, our common sense check, the ends are about 250. The long parts are 40 times 10, about 400. So you multiply those together and add them up, you get around 1,300, which is about what we had, okay? So again, these common sense check to make sure that what we're doing makes reasonable sense. So we're just going to work through some more practice problems. I've got 8 more here on this PowerPoint. These are all actually physics ones. They're a little bit shorter than the 2 that we just did, and they're involving physics equations. The physics equations on the bottom of that practice page that I showed you. But again, we need to practice this. This is a skill. Looking at the problems, figuring out how to solve the problems. So again, I would encourage you to pause the video when you see the new problem, work through it, and then see how I do the problem once you've finished it. I'm not going to be taking any breaks. I'm just going to talk my way through these problems because I know you're watching a video and you have the ability to pause it in between the individual problems. So how far has a car traveled if it started with a velocity of 5 meters per second, accelerates at 3 meters per second squared, and travels for a total of 10 seconds? So this is a more typical problem. You're just given it all written out. So you could draw a little picture of a car driving down the road, and you can record all your givens, right? I was given 5 meters per second as an initial velocity. So here's a case where we use a subscript, right? There's an I. Sometimes you see an O because we start counting at 0, I because it's initial. The point is we want to distinguish that this is the starting velocity. And this is important when you have an object that is accelerating. Acceleration is how you change your velocity. So we need to know where we started at if we're going to be addressing the change. So we have an initial velocity of 5 meters per second, an acceleration of 3 meters per second squared, and a time of 10 seconds. That is simply a matter of writing down the numbers in the problem, some of which were described. Starts with a velocity, so that would be initial velocity, acceleration, and then 10 seconds, the units imply clearly that the 10 is a time, okay? And now we're being asked for a how far, so we're being asked for the distance. So this is my unknown, these are my knowns, and so I've written down my knowns, and I've written down my unknown, and I'm gonna try to find now an equation that has all of those together. So I'm looking at that sheet, looking for something that has D, VI, A, and T. And this is what we have, right? The one that we had discussed on an earlier slide. D equals VIT plus 1/2 AT squared. The nice thing about this equation is that it's already solved for our unknowns. So we don't have to do any more algebra to it. The unknowns on one side and all the things that we have values for are on the other. So we can just directly go to the solving step, where we plug in our initial velocity of 5, our time of 10 into VI times T. We plug in our acceleration of 3, we plug in our time of 10, and we remember to square it. So 5 times 10 is 50, 1/2 of 3 is 1.5, 10 squared is 100, 1.5 times 100 is 150, 50 plus 150 is 200 meters. And if we think about that, the common sense here is a little more challenging if we're not as familiar with meters and seconds, right? But we know we started out going 5 and we're speeding up from there, right? A positive acceleration means we're going faster. So if we accelerate at 3 meters per second squared for 10 seconds, that means we're going to end up 30 meters per second faster than where we started. So 35 and 5, you would average those out and you would get 20, right? 35 plus 5 is 40. 40 divided by 2 is 20. So our average velocity is 20. If we go 20 for 10 seconds, 200. So the common sense check gives us exactly the same answer that we had. So another car problem. If the average velocity of a car is 15 meters per second, the final velocity was 22, what was the initial velocity? So a little bit different problem here. It's all about velocities, and it's focusing on this idea of average. So we don't know what the initial velocity is. That's our unknown. We do know that the final velocity, right? So here's a subscript that's an F that stands for final. And here's a subscript that's AVG, which stands for average. So our initial velocity we don't know. Our final is 22, and our average was 15. So we have 3 velocity numbers. So we're looking for an equation that has initial, final, and average velocity in it. And this is what we get. The average velocity is equal to the sum of the initial plus the final divided by 2. Initial plus final velocity divided by 2 equals the average. This is assuming a constant acceleration. We always make that assumption when we're doing kinematics in introductory physics. To have variable accelerations requires calculus to solve the problems, and that's beyond the scope of this course. So that's why we have this average equation. Obviously, that does not work in other areas, right? You don't take your first test score and add your final test score and divide by 2 and well, okay, so 2 test scores, that works. But it does not work unless you have the assumption of a constant change in between. Well, I should say, yeah, your initial and final test score does not tell you what your total test average is because there were other tests in between, and you don't necessarily have the same degree of improvement or between each set of tests. So this is the equation. We already have the average, so we need to solve for the initial velocity, right? So we bring the 2 to the other side. So we have 2 times the average velocity. Oh, funny, I forgot the V. 2 times the average velocity, because we multiplied both sides by 2, which dropped that 2 out and brought a 2 to the other side. And then we subtract the final velocity to leave the initial velocity all by itself. So 2 times the average velocity minus final velocity equals VI. So VI is 2 times 15 minus 22, and that gives us 8. So again, if you want to do a common sense check, if you want to check this, you can stick the 8 back into the equation, right? 8 plus 22 is 30. 30 divided by 2 is 15. So if I stick in the 22 and my 8, I end up getting the 15 back. So that's another way to check your answer, is to plug it back into the original equation. All right, so the third problem. A rock is dropped from rest from the top of a cliff, accelerating at 9.8 meters per second squared. What is the velocity after 3 seconds? So this is going to be a common problem we're going to deal with. We talk about gravity a lot in physics. Gravity causes things that are dropped to speed up as they fall downward. And so here's an example problem like that. We're given the acceleration, we're given the time, we're being asked for the velocity. So we're also being told the initial velocity. Here's one of those cases where we're given non-numeric initial information. A rock is dropped from rest. Okay, so that means our initial velocity is 0, and that's important to recognize from those words. A rock is dropped from rest. And again, we have the life experience to understand that that if you drop a rock, it's going to start out when it leaves your hand with 0 velocity. So we have initial velocity is 0, acceleration is the 9.8, time is 3 seconds, and we want to know what VF is. So we have this equation, VF equals our final velocity equals our initial velocity plus however much we accelerate the rate at which we accelerate times how long we accelerate at that rate. And it is already solved for VF, which is what we want to know. So we can go ahead and stick our numbers in. 0 for initial velocity, 9.8 for our acceleration, 3 seconds for our time. 0 is obviously 0. We love the number 0. We'll get into that more later. This second is going to cancel with one of the seconds in the denominator. Remember, seconds squared really means second times second. So a second in the numerator will cancel one of those out. And we'll multiply those numbers together and get 29.4 with the meters still and one of the seconds. So 29.4 meters per second for our final velocity, which should be in distance over time because it's a velocity, right? A common sense check here would be to just round 10, 9.8 up to 10. And if we're accelerating at 10 meters per second squared for 3 seconds, 10 times 3 is 30, and our answer is about 30. A bike problem. If a bike travels 45 meters while accelerating at 1 meter per second squared for 5 seconds, what was its initial velocity? So again, what have we been given? We've been given a distance, we've been given an acceleration, we've been given a time, and we're being asked what was its initial velocity. So VI is the unknown, our distance is given, our acceleration is given, our time is given. Those are our known things. Might look familiar to you. Problem 1 was that same set of stuff, only in problem 1 we didn't know D and we knew what VI was. But that same set of variables, VI, D, A, and T, will mean that we'll use that same equation. D equals VIT plus 1/2 AT squared. This time, though, we're going to have to solve it, right? It's solved for D. We want to solve it for VI. So to do that, we're going to first subtract the 1/2 AT squared part to the other side. So we would have D minus 1/2 AT squared. And then to get VI all by itself, we need to divide everything by T. When we do that, we get D divided by T. And we get 1/2 AT squared divided by T, but that T just cancels one of the T squareds. So we end up with VI equals D over T minus 1/2 AT. So that's the algebra. I did not show that as explicitly, but hopefully you can follow what I said there about how we solved for VI. So our distance, now we get to plug in our numbers. Our distance was 45, our time was 5. So 45 divided by 5 is 9. 1/2 of 1 is 1/2 times 5 is 2.5. And we're subtracting. So 9 minus 2.5 is 6.5 meters per second. Again, you can go back and plug them in. 6.5 times 5 will give us 32.5 plus 1/2 of 5 squared. 5 squared is 25, or 1/2 of 1 of 5 squared. So that's 12.5 plus 32.5. That comes out to be 45 meters as we expect. So again, that's one of the ways. I mean, I described it in the problem solving process as a common sense check, but you can also consider that a check of plugging back into the original equation and making sure you get your original answer back. So how long will it take a bus to travel 450 meters if its average velocity was 40 meters per second? So this is actually a very simple one. Anytime we are dealing with an average velocity, it's the same as if we were dealing with a constant velocity. So we don't know T, but we know V average and we know D. So we have that very simple distance equals average velocity times time equation. We need to solve it for T by dividing both sides by average velocity. So we get distance divided by average velocity equals time. So 450 divided by 40 gives us 11 seconds, right? Only two digits, 2 significant digits in these problems. So we rounded our time to 2 significant digits, 11 seconds. And again, if we think about that, 40 times 11 would come out to be 440. So that's approximately our answer back. Motorcycle traveling down the highway 45 meters per second. Then the rider sees a police officer 4 seconds later, he's traveling a little slower. What was its acceleration during those 4 seconds? So we have an initial velocity, right? It's important to note the description where it talks about seeing a police officer and then later. So the velocity we were given to begin with is initial, and the velocity we're given later is final. So initial velocity, final velocity, and a time, and we're supposed to be solving for acceleration. So we've got A that we don't know, VI, T, and VF that we do know. Again, what we know and what we don't know is really less important in terms of choosing the equation. We just need an equation that has A, VI, T, and VF in it, okay? We will then end up solving that equation for the one we don't know. So we have A equals VF minus VI all over T. So that's, again, one of the equations from your sheet. This is a description of acceleration, which again, we'll go into more what acceleration really is in chapter 4, but it's our change in velocity over time. It's already been solved for A, so we stick in our numbers. 30 is our final velocity, 45 is our initial velocity, and 4 is our time. So we stick them in, we divide, we get an answer that is negative. Again, both of these are in meters per second. So when we subtract them, we get meters per second. We divide by another second, so we get meters per second squared. And it's negative, right? He saw the policeman, and so he's slowing down. And we'll talk about how slowing down is actually negative acceleration because his final speed is less than his initial speed. So now we got a rocket problem. A rocket is fired straight up with an initial velocity of 56 meters per second. Gravity is accelerating it downward, which we're going to call negative because we called the initial upward velocity positive. Negative 9.8 meters per second. What is its velocity after 4 seconds and after 7 seconds? So really here we have two questions that we have to answer, but we're going to end up using the same equation because everything is the same except for the time, and we just have two different times to plug in. We were given an initial velocity, we're given an acceleration, and we're asked for a final velocity. And we're given a time. Actually, we're given 2 times. So we're going to come back to this equation where V final is V initial plus AT, which we used before, and it includes all the variables that are given or unknown in the problem. It's already been solved for VF, so now we just have to plug in our values. 56, a little fast. 56 plus negative 9.8 times 4, so this is the first problem. So after 4 seconds, we're still going up. Okay, so we have the initial velocity of 56. We're looking for that final velocity. So we have VF equals VI plus AT. Solve for VF already. So it's 56 plus negative 9.8 times 4 for the first one. So at the end of 4 seconds, we are still moving upwards, but we're not moving upwards near as fast, right? Gravity has slowed us down on our way up. But after 7 seconds, we actually have a negative velocity because gravity has succeeded in slowing our rocket to a stop, and we are now starting to fall back down. So at 4 seconds, we're still going up, but at 7 seconds, we have a negative value and going back down. So train is traveling at 35 meters per second when it applies the brakes. 95 meters down the track, it is only traveling 25 meters per second. What is its acceleration? So again, we are given an initial velocity, we're given a final velocity, we're given a distance, and we're asked for an acceleration. This is a somewhat unusual problem. The vast majority of kinematics equations involve time. Time is either known or time is being sought. This is a rare problem where time is not given and time is not asked for. So the equation that we use here looks a little unusual compared to the other ones. It doesn't have a physical interpretation as easily as the other ones do. It comes from substituting in one of the other ones solved for time into another equation. But that's not important to us ultimately for problem solving, for solving the problem. we have the equation. Here it is, 2 times acceleration times distance equals vf squared minus vi squared. So that's the equation. It has a, vi, d, and vf. It doesn't have a t, and we don't know t, so that's fine. We do need to solve it for a, which means we need to divide this side by 2d to get a all by itself. So we end up with vf squared minus vi squared over 2d equals a. And then we can go ahead and plug our values in. 25 squared minus 35 squared. Notice the order of these is extremely important. If we switched these two, that would change the sign of our answer. But our train is applying the brakes, and so it's perfectly appropriate for us to end up with a negative acceleration because our train is slowing down. 25 squared minus 35 squared all over 2 times 95 ends up giving us negative 3.2 meters per second squared. So if we think about, okay, we're going from 25 down to 30. So you average those, we'd have an average speed of 30 meters per second. We're going from 35 down to 25. So we averaged 30 meters per second. If we went 95 meters and we were averaging 30 meters per second, that means it would have taken us about 3 seconds, a little over 3 seconds to slow down. Or to travel that distance. We've been traveling for 3 seconds. So if we're going to slow down by 10 meters per second in a little over 3 seconds, that would be 10 divided by 3. 10 divided by 3 would give us about negative 3 1/3, right? So that's our common sense check for that one. So hopefully these problems, practice problem solving, has been helpful to you. Again, you have homework, you'll have a quiz, you'll get more practice. Again, I would encourage you to look at examples from the book. This is a very important skill, which you will get practice with all through the semester, because physics is a lot of problems that need to be solved. So I will see you next time with chapter 3.